Hello, my name is Krzysztof Chojnowski and I'm a senior support engineer at SOMLabs. Welcome to the first part of our webinars concerning the NXP Yocto system and Vision SOM8 Mini modules with Vision CB8M STD carrier ports. We will start today's meeting with getting to know the development environment we have prepared for you in the form of a virtual machine. Then we will move on to the Yocto receipt structure and the layer providing the support for Vision SOM modules created by SOMLabs. Next, we will discuss in detail how to build a system image along with the SDK for compiling programs on the host machine and install the prepared system on the target hardware. At the end, we will show you how to compile and run a simple application written in C language and how to include it in the mechanism of building the entire system image. During this workshop, we will have the opportunity to perform several practical exercises. The necessary sources are located in the Home Dev Exercises Workshop 1 directory on the virtual machine that we prepared for you. They will concern in turn compiling the program using the build SDK, creating a new recipe, and configuring system scripts that run the user's application automatically during startup. We will perform all tasks on a shared virtual machine running on Ubuntu 18.04 host system. Alternatively, the whole environment can be prepared on your own machine, which will also be discussed in the presentation. So let's start by configuring and running a VirtualBox machine on which we will perform all the exercises. For this we need the Oracle VirtualBox version 6.1 with the extension pack installed. Everything is available at virtualbox.org website. The machine disk file requires 165 GB of free space, so make sure you have a sufficiently large disk available on the host machine. We can log into the running virtual machine with the login dev and password dev. During the exercises, we will only use the SSH connection, so you need to set up VirtualBox's network interface as bridged network adapter. Now in the video we will show you how to connect the machine to the VirtualBox step by step, configure it and run it. So let's go through the entire process of setting up the virtual machine for this webinar. In the VirtualBox graphical interface, we can add an existing machine by clicking the Add button and selecting SOMLabs VBox. To access it in the local network, configure the network interface as a bridged adapter, pointing to one of the host interfaces. Here we select the Ethernet wired network. We can now start the machine and wait for the system to boot. After starting the system, open the terminal and use the IPA command to verify that the machine is connected to the network and if the IP address has been correctly assigned. With this address, we can connect via SSH from the terminal on the host. Alternatively, instead of the IP address, we can also use the machine's network name, so somlabs.local. Using both addresses, we can connect via SSH and move on to further exercises. The Ubuntu system installed in the virtual machine is already configured and the Yocto image has been built and is ready to be installed on the target device. However, before we go into that, we will briefly discuss the entire build procedure, as it will be useful later when we make changes to this configuration, and so that you could easily create it on another computer. The manual has been prepared for Ubuntu 18.07. First of all, we need to make sure that we have a set of necessary tools and libraries in the system. Freshly installed Ubuntu does not have the appropriate packages, so we have to install them via apt-get install as shown on the slide. The second step is to prepare the environment for building the Yocto system. First, we create the I.MX8M BSP working directory. In this directory, we will have all the sources and we will work on it to apply changes to our system. Now we can download the sources using the repo tool, which makes it easier to work with multiple repositories. Thanks to it, with a single repo init command, we can get everything that is needed for compilation. The sources are downloaded from source.aurora.org, where NXP has posted all the layers and libraries necessary to build Yocto for NXP processors. When fetching the sources via repo init, pay attention to the version name, Zeus in this case. Another command, repo-sync, synchronizes our sources with the remote repository to work on the latest version. Having the source from NXP downloaded, we still have to download the layer that introduces support for VisionSOM modules. We do this by copying the repository with git clone from SOMLabs GitHub site. Note again the compatibility of the version Zeus with NXP sources downloaded before. The full git clone command is shown on the slide and you can copy it and execute it yourself. Adding a new meta-SOMLabs layer requires modifying the I.MX setup release sh script, which puts the necessary information in other configuration scripts like bblayers conf and localconf. At the end of the script, we add the lines shown on the slide. In the same place, we can also add the commercial license needed to build video libraries used in the default image for VisionSOM8M Mini by the demo application. In the next step, we define the machine for which the system will be built. In this case, VisionSOM8M SDK described in the meta-SOMLabs layer. The distribution, FSL I.MX Wayland, and the directory where the compilation will take place. The mentioned machine was prepared for the VisionSOM8M module and the VisionCB8M STD carrier board. The command shown on the slide configures the shell, copies the necessary scripts and goes to the build directory. At this point, we can start the long compilation process by calling bitbake FSL image validation I.MX. This command may take up to several hours depending on the available hardware resources on host machine. For this reason, everything has already been built on a virtual machine and you do not need to build the whole thing for the webinar, only the changes that we will apply later during these exercises. To build the SDK, which also has already been done, you need to add the -c populate SDK option to the bitbake command. This way, we will get an SDK package that we can install on the host and we will have access to all necessary tools and libraries to compile the application for the VisionSOM target device. After the build is complete, the system image is located in the TMP deploy images directory and the SDK in the TMP deploy SDK directory. The detailed instructions for building the current version of the system can be found in the SOMLabs repository in the README file and on the SOMLabs wiki page. Having all the sources for building the system downloaded and prepared, we can move on to discuss the structure of recipes that make up the Yocto system. Recipes are arranged in meta layers, as we can see by browsing the sources directory downloaded from the NXP repository. Meta layer and recipe directories are added to the build process as needed, as we will see in one of the next parts of the workshop when we will add our own recipe to the system building process. For now, let's take a look at an example recipe, Linux I.MX, containing instructions for building the Linux kernel provided by NXP. It is located in the sources meta I.MX, meta BSP, recipes kernel, Linux directory, and it contains two files with the extension bb. These are the base recipe files for building. Looking at one of them, Linux I.MX54bb, we will notice that in addition to a general description, there is also information about the kernel code repository, its version, and dependencies needed to build this component. Please also note the file name that contains the kernel version 5.4. Thanks to this format, we can define subsequent bb files with other versions of sources and select them depending on the configured target machine and the required version of the package. Recipe files can also be inherited, as we will see in a moment when we will discuss the structure of the SOMLabs layer. The layer provided by SOMLabs allows us to build the Yocto NXP system for the VisionSOM modules. This support is currently available for both the older VisionSOM 6 ULL and the newer I.MX8M Mini with the corresponding carrier boards. The layer provides definition of machines in the configuration files, patches applied to the kernel and bootloader, and demo application prepared by SOMLabs. The purpose of the SOMLabs layer is to enable an easy creation of a system image along with the graphical environment and support for selected interfaces. When browsing the layer files, we find a number of directories. These are among others conf with a formal description of the layer, for example its priority in relation to other layers and the Yocto version for which it was prepared, and definitions of machines added by it. Recipe directories with bb append file that extend or change the procedure defined in basic bb files, and a directory with recipes added by SOMLabs, in this case with demo application. The machine definitions located in the conf machine and conf machine include directories. Files are divided due to the hierarchical structure and the possibility of including files common for individual models. The file in include directory describes, among others, architecture, CPU type, memory, and bootloader configuration. In the VisionSOM8mm cbstd.conf file, we also have a definition, the device tree for file defined for the kernel. In the machine configuration, we can also add additional packages for installation, for example with support for wireless modems. The recipe file extensions with names ending with bb append introduce changes to the code repositories, because SOMLabs provides its own versions of U-boot and kernel based on the NXP releases and containing the necessary patches to add support for Vision SOM hardware. This can be seen in the files U-boot I.MX8M append and Linux I.MX8M append in the variables containing links to the repository and code revision numbers. Moreover, we can see that the build procedures can be performed conditionally depending on the defined and selected hardware. In the kernel recipe, the configuration file is selected this way. The do copy SOMLabs devconfig procedure performed after the do patch and do copy devconfig procedures and before the do preconfigure procedure is responsible for this. All of the mentioned procedures are defined by NXP base recipes. The base do copy SOMLabs devconfig procedure is empty, but depending on the Vision SOM8mm or 6ULL configuration selected in the machine build process, a code fragment selecting one of the two configuration files is added to it. The complete code of the procedures is dynamically created by the bitbake build system based on the keywords such as append, prepend in the name of recipes and by the machine names. After learning the general structure of recipes and the hierarchy of directories in Yocto, and after building the system image which we discussed earlier, we can move on to the installation and first launch of the system built for Vision SOM modules. Assuming we are using a provided virtual machine, we should first copy the compressed system image to the host using the scp command. It is shown along with the path to the image on the slide. After copying it to the host, we should unpack it with the bunzip2 program available on Unix systems. The unpacked file contains a memory image that we can copy directly to the SD card, if we have a module equipped with this type of memory. We can copy the image file to the SD card using the dd command as shown on the slide. During webinars, however, we deal with the modules with eMMC memory, so we will now focus on installing the system in this version. First, we will need the universal update utility, which we can download from the NXP website as a binary file or use the sources in the NXP repository in order to compile it ourselves. Detailed compilation instruction can be found in the README file of the MFG-Tools repository. The universal update utility needs an unpacked image, we have it ready, and a compiled bootloader. It is built together with the image, so we can download it from the virtual machine, just like the image archive. It is a file with the bin/flash EVK extension. Having both files, so the system image and the bootloader, run the UUU command. Superuser permissions are required. The utility installs everything on the device's eMMC memory. After starting the update utility, we get a message informing us about waiting for known interfaces. At this point, we need to connect the powered Vision CB8M STD board to the computer using the USB OTG connector. Then press the reset button, and while holding it down, also press the boot RCRV button. Now release the reset button while holding the boot RCRV all the time. At this point in the terminal, the application will inform us about programming the memory. We can release the boot RCRV. This process may take several minutes, and when finished, the application update will also exit. Now we can change the USB OTG port to JLink console socket and connect to the appropriate port using one of the programs such as Screen or Minicom. The name of the port may of course be different for our host system, but it should be one of the TTY ACM ports. The baud rate should be set to 115/200. On the carrier board there is a programmer that needs some time after connection for proper initialization before we can boot the system and use the serial port. After waiting for a few moments required by the programmer to initialize, we need to reset the board with the reset button, and in the terminal we will see first the bootloader logs and then also the ones from the kernel. At the end of the boot process we can log in as the root user without a password and check the system version with the uname-a command. If we also have connected the board to the local network using an Ethernet cable, we can log in via SSH. Then we can read the assigned IP address with the IPA command in the serial terminal. For SSH connection we can use this address, which changes every time the system restarted, or by using the network name of the device, Vision SOM8M std.local. In one of the previous steps, we had the opportunity to build an SDK, thanks to which we can compile programs for the target hardware, which is of course Vision SOM8M Mini. This can be built on any PC with this package installed. In the virtual machine, the SDK is installed in the OPT FSL I.MX Wayland 540's directory. In order to use it, we must first configure the shell we are currently in. The environment setup arch64 Pokey Linux script is used for this. When invoked, it allows us to use the compiler and libraries, thanks to which we will build the first program in C. The source code of a simple program is located in Home Dev Exercises Workshop 1 Lab 1. We can compile it using the cc environmental variable, which we will do in a moment. So let's follow the entire process of compiling the program. First we configure the shell with the environment setup arch64 Pokey Linux script, and we can check the compiler version to make sure everything is set up correctly by calling cc-v. Then we use the cc to compile the main C source file. The resulting binary file can be checked with the file command. It informs us that it is an executable file for ARM64 architecture. Finally, we can copy the binary file to our device using the scp command. We can do it directly from the virtual machine. Next, log into the device via SSH or via the serial port and run a compiled application. The program will display Hello Vision SOM in the terminal, which means that it works properly. The presented method for compiling and preparing the application for the target platform is of course correct, but the application is not added by default to the build system image and requires separate copying after each image file installation in the target memory. To enable automatic compilation and installation of your own application in the system file in the memory of the device's SD card or eMMC memory, we should create a recipe that will be built with all other components included in the image. We will place our new recipe in the meta SOMLabs recipe SOMLabs directory, similarly to the SOMLabs demo application. The new recipe contains the bb recipe file and the program code main C, located in a subdirectory with the same name as the recipe. This file is not downloaded from an external repository but is provided with the recipe as a source file. All these files can be found in the Home Dev Exercises Workshop 1 Lab 2 directory, from where they can be copied directly to the recipes SOMLabs directory of the Meta SOMLabs layer. The main C file is different from the previous one. This time, after running the program, the LED marked as IO05 on the carrier board will blink 3 times. We can control it by writing values 1 or 0 to the file sysclass LEDs LED IO05 brightness, which we will see in the application code. The program opens the mentioned file, writes the 0 and 1 values to it, and finally closes the file and finishes its execution. In the recipe file, we will find information about the files used, in this case only main C, and 2 procedures. The first one, to compile, contains the command that we have already used to compile the first example. The second procedure, to install, creates the directory usr share SOMLabs example in the file system of the target device and copies the compiled program binary there. For a recipe to be used during a build, it must be included somewhere in the compilation process. We will use the package install variable located in the file meta SOMLabs recipes FSL images FSL image validation I.MX8M append. After adding a new recipe to the list, we need to rebuild and install the entire system image as discussed earlier. After starting the system, we will see that our program is in the mentioned directory. The application can be started manually after logging into the newly built system version. We can also observe the changing state of the LED on the carrier board. The last exercise that we will do during this meeting is to configure our own application so that it starts automatically after system startup. For this, we have to slightly modify the recipe from the previous example. The new version of the recipe with all sources can be found in Home Dev Exercises Workshop 1 Lab 3 directory in the virtual machine. We can copy it from there, replacing the previous files in the Meta SOMLabs recipes SOMLabs example directory. We can now see the new file structure on the slide. In addition to the sources we discussed previously, we now see a new file, SOMLabs example service. It is a service that starts automatically after system startup, which runs our application. We will discuss it in a bit more detail in a while. We need to add a new source file, SOMLabs example service, to the recipes BB file, and an entry inherit systemd to allow the addition and configuration of the startup script. And then we use the systemd auto enable variable to decide whether the startup script should be enabled by default and give it a name in the systemd service pn variable. Pn is the package name, which is of course SOMLabs example. We also add the service file in the install procedure next to the binary file of the application. The script itself defines the way the application is launched. In this case, it is only launching the SOMLabs example binary and introduces dependencies on other services and units. Our service will depend on the multi-user target unit and will run only when it is also started, which in turn will happen automatically on boot when the Linux shell is ready. After rebuilding and reinstalling the system, our application will be launched automatically, which can be seen by the IO05 LED flashing 3 times. This is where we end the first part of the workshop series. In the next part, we will modify the Linux kernel and the device tree to add new drivers and communication interfaces. Thank you very much for your attention.